Okay, good morning. Today we'll look at C amplifiers. So we have about 23 minutes left. And we'll look at this as a separate chapter, BJT amplifiers. So this is also the design lab that you'll be doing this week, common emitter amplifier. So what I like to do is go over the basics of a C amplifier configurations, and then do a load line analysis problem. And then when you design, you'll use the load line for your designs. Now, the earliest lab is on a Wednesday. Design is not something we'll get until the Wednesday class. So the pre-lab can be submitted sometime later. It's fine. I'm trying to figure out a way on how to fit it within the time that we have. I think the best way to do this is to either write out the instructions, or I would have you just watch the video from one of the previous lectures so that you can do the pre-lab and the design, before lab class on Wednesday. For the students who have lab class on Thursday, I guess it doesn't matter. Okay, but the students who have lab class on Wednesday, you need to know how to do the design of the C amplifier. All right. Okay. So common emitter amplifier. Standard configuration is shown here in this image. You have two power supplies, VCC and VBB. In reality, of course, we use a voltage divider bias so that we do not have to use two different power supplies. Typically, this circuit could also be shown like this. You have plus VCC. You might have a minus VEE or simply ground at the emitter. And then you'd have the base bias VB or VBB. And your AC input also goes into the base. So this is the configuration for a common emitter BJT amplifier, CE. Okay. And then you have RB, RC, and RE, three terminal resistors. So the DC voltages that you apply, VCC, VBB, and VEE, if you choose to, the DC voltages must bias the BJT operation in the active region. Otherwise, it will not work as an amplifier. It will simply work as a switch. Hence, DC biasing is very important. That's the first step you would take for amplifier. If it's not biased correctly, circuit's not going to work. I mean, circuit will work, but our output will be distorted and clipped. Okay. Cutoff and saturation. In cutoff and saturation, it functions like a switch. So the ground symbol that is shown here does not have to be physical ground. It's basically references. It's the single reference point in the circuit. Okay, all other voltages are measured with respect to this point. Now, BJT is in cutoff, the switch is off. In saturation, the switch is on. No, the two operating modes combined, we say that it acts like a switch, like a digital switch. Yes. When it's in cutoff, current is off, voltage could be high. When it's in saturation, current is high, voltage is almost zero. Yeah, that's where it works as an amplifier. And we will see that in the next 2 slides. All of the power for this amplifier comes from the DC biasing voltages. So on the output side, which is the collector terminal, that's where the DC voltage VCC controls the output. Okay. So the AC input is coupled or injected into the base, is applied to the base, and output is collected or output is received at the collector. Okay. One other thing we need to keep in mind is the notations. So lowercase notations with uppercase subscript means AC and DC combined. Let's make this a bigger font. So that's a lowercase v. That's an uppercase v. VB. Remember from first chapter 1? IB. This is AC plus DC. Okay. The DC value, of course, comes from the power supply's VCC. So every amplifier output will have a DC component built into it, just because of the way the circuit is designed. The AC input is applied to the base terminal, and then the output changes according to the input signal that's applied. So V in, which is the AC input, or V in of T, is very, very small. Okay, V in of T is very, very small. So there's a whole branch of analysis of these devices, electronic devices, which we refer to as small signal analysis. Okay, these are nonlinear devices. So these nonlinear devices, if you wish to apply linear analysis techniques to this, to any nonlinear device, we take a small portion of the signal and we assume that it might behave linearly for that small portion. So the AC input signal applied is very, very small. The analysis that we do for these small AC input signals is known as small signal analysis. So later on in this chapter, we'll look at what constitutes small signal analysis and what constitutes large signal analysis. Okay, yes. Where? It's not an offset. The DC voltages are the biasing voltages applied to the BJT. Those are not offset. Those are just the DC voltages that are applied. It's not an offset. I mean, it results in an offset, yes, but that's not an offset. That's not what we call it. Again, amplifiers, whether op amps are built out of BJTs, transistors, and MOSFETs, right? We say they're amplifying the signal. Well, if you apply 1 volt to it and the gain is 10 volts does not magically appear at the output. The amplifier must have a power source. that power source comes from the DC power supplies. The whole point of amplifiers is to take a time varying signal, meaning AC signals, and amplify it or make it larger, to put it in the simplest of words. But the power, the voltage, or the current that is associated with a large signal does not come from empty air, right? It does not come from thin air. It comes from the DC biasing voltages. So you have AC input coming in, you have the large DC signal being applied to it. In reality, what is happening is the device, the BJT or the MOSFET or whatever device you're using for amplification, is taking the input signal, is taking the DC power, and it's giving the shape of the AC signal to that DC voltage supply. DC is a flat line. DC is a flat line. Large value, let's say 10 volts or 15 volts. And your AC input signal is this small. And this is a very simplistic drawing, of course. And that's your AC signal. The BJT device or the amplifier device is taking these two signals and giving the shape of your AC signal to this large DC signal. So now the output has an offset or has a DC component. The input side, it's not. Input side is just coupling. And you will see in the next two slides. Yes. No, it will. Depends on what VBB is. That's when our transistor, if your design is not not in the middle of the active region, it could move it towards saturation or it could move it towards cutoff. Cutoff, saturation. All right, common emitter amplifier. What do we see here? We have two graphs, one for the input side, one for the output side. Okay, input characteristic, meaning the base emitter characteristic, and the output characteristics, meaning the collector emitter characteristics. Input side is a forward bias PN junction, so the characteristics look like a forward bias diode. Output side, we are ignoring the resistance and just saying it's flat. Otherwise, they would actually curve up. Right? So we're ignoring that. Doesn't matter what the characteristics are. The analysis, the load line analysis remains the same. What we would do is we would apply KVL on both sides. We apply KVL to the input side. We apply KVL to the output side. And we generate our load line to obtain 2 points on the input side. And then we generate a load line on the output side. Okay. And then we use this to solve for the AC input signal. So if you apply KVL on the input side, if you want to determine the load line, simply apply KVL. You obtain an expression which has both the input voltage and the input current, right? This is the input voltage, VBE. This is the input current, IB. On the output side, we have voltage VCE, and we have current IC. Okay, so you want to generate an equation that has both of these quantities in there. So KVL for the input loop gives us minus V in of T plus VRB plus VBE minus VBB equal to 0. V in of T would be known to us. VR would be known. Our VRB is IB times RB. So we can rearrange the equation to give us V in of t plus VBB, the supply voltages and the AC input signal, is equal to IBRB plus VBE. So again, this would be given or known to us. This is also known or given. If to find the 2 points, we substitute IB is equal to 0. So if IB is equal to 0, then VBE is equal to the supply DC supply voltage at the base plus the AC input signal. And if VBE is equal to 0, then IB is excuse me, VBB plus V in of t divided by RB. Okay, divided by RB. Taking it further, if there is no AC input signal applied, then VB is equal to VBB and IB is equal to VBB or RB. Those are the 2 points for the input load line. All right, we just have about 30 seconds left, so I'm going to go through this. If you have to leave at 12, you can leave at 12. KVL on the output side. Minus VCE minus VRC plus VCC is equal to 0. Therefore, VCE is equal to VCC minus ICRC. For the 2 points of the load line, plug in VC is equal to 0. IC is equal to VCC over RC. And if IC is equal to 0, then VCE is equal to VCC. And that's it. And these are the 2 points for the output load line. Okay, output load line. Okay, let's end class here today, and then we'll pick up here again on Wednesday. We'll go through the rest. You have access to the previous quarter's videos. So as a reminder, I'll post an announcement with a single link to the video, but check out the video for the design of a C amplifier using load line analysis, right around this week 9 timeline. Okay, you will need that in order to design for lab 8, which we will continue with on Wednesday. All right. In the meantime, if you have any questions, feel free to ask.